Pluto was once thought to be a planet in our solar system, but it is still a distant and fascinating celestial object. Recently, well-known astrophysicists like Neil deGrasse Tyson and Michio Kaku have brought Pluto back into the scientific spotlight, proposing a startling new theory about the possibility of Pluto colliding with Neptune. This raises a number of important questions about how such a catastrophic event could happen and what consequences it would have. 35 seconds investigating the potential impact of a Pluto-Neptune collision. Pluto, once classified as a planet but later redefined as a dwarf planet, continues to captivate the scientific community. Its unusual orbit makes it a subject of ongoing research. According to recent discoveries from leading scientists, Pluto's orbit crosses dangerously close to Neptune's path, raising alarms about a possible collision. But how feasible is such an event? Pluto's journey around the Sun is unique among the planets. It takes 0.01 and 8 seconds am lengthy 248 years to complete one full orbit. As a result, since its discovery in 1930, Pluto has not yet finished a single full orbit. In addition to its long orbit, Pluto's path differs significantly from the nearly circular orbits of the other major planets, as it is tilted at a 17 degrees angle relative to the plane of the solar system. This results in a much steeper trajectory compared to the other planets. A particularly fascinating aspect of Pluto's orbit is its periodic intersection with Neptune's orbit. For 1 minute and 42 seconds, approximately 20 years in each orbit, Pluto is closer to the Sun than Neptune, which is surprising given their positions in the solar system. This naturally leads to the question, why has Pluto not collided with Neptune? The answer lies in the gravitational forces of other planets. When astronomers first studied Pluto's orbit, they were confused by its unusual characteristics. Unlike other planets, whose orbits mostly lie near the ecliptic plane, Pluto's orbit is tilted and curved. This anomaly raised even more questions when 2 minutes and 15 seconds astronomers realized that Pluto's path intersects Neptune's. Studying this occurrence illustrates the complexity of space dynamics, especially when multiple celestial bodies influence each other's motion. The three-body problem in space is a challenge that describes the difficulty of predicting how three celestial bodies, such as Pluto, Neptune, and the Sun, interact gravitationally. Pluto's orbit is chaotic. Even the smallest variation in its initial conditions could lead to dramatic changes over time. However, this chaos has 2 minutes and 49 seconds been found to stabilize over long periods. Simulations have shown that the gravitational pull of larger planets like Neptune, Jupiter, and Saturn prevents Pluto's orbit from destabilizing over billions of years. Without these larger planets exerting their gravitational pull, the solar system would be much more chaotic. Pluto's orbit is a clear example of both disorder and stability in celestial mechanics. Although its path is irregular, it has surprisingly remained stable due to 3 minutes and 21 seconds gravitational influences exerted by neighboring planets, particularly Neptune. Predicting the future behavior of such an unstable orbit as Pluto's is extremely difficult due to the inherent unpredictability of these systems, which makes long-term forecasts uncertain. This leads us to the question of why respected astrophysicists such as Neil deGrasse Tyson and Michio Kaku are now sounding the alarm about a potential Pluto-Neptune collision. Despite the stabilizing forces being well 00:03:56 understood, the possibility of such a collision, should it occur, would be catastrophic. The collision would release an immense amount of energy, most likely obliterating Pluto due to its smaller size and icy composition. The resulting debris from the impact could be scattered throughout the solar system, potentially endangering other planets and their moons. For Neptune, the impact could affect its atmosphere and even alter its orbit, depending on the scale of the collision. Kaku, a theoretical physicist known for his work in string 4 minutes and 28 seconds theory and space exploration, provides a unique perspective on the situation. His knowledge of orbital dynamics and gravitational interactions enables us to appreciate the deeper connections between theoretical physics and celestial mechanics. Understanding how bodies like Pluto interact gravitationally is essential for future space missions because it not only aids in exploring distant planets but also helps predict and prevent potential dangers within the solar system. The effects of a Pluto-Neptune collision extend far beyond Pluto itself. 4 minutes and 58 seconds. Beyond the immediate destruction of two celestial bodies, it could also provide crucial insights into high-energy physics and gravity. The event might create conditions where string theory predictions become observable, offering explanations for how fundamental forces and particles behave in extreme environments. While the physical impact on Earth would be minimal given the vast distance between Pluto and our planet, the scientific consequences could be monumental. It would provide a rare opportunity to observe and test key 5 minutes and 27 seconds principles of string theory and other branches of physics. With its steep inclination and tilted orbit, Pluto defies conventional planetary motion. Unlike the nearly circular orbits of the major planets, Pluto's orbit intersects Neptune's, complicating predictions about future interactions. The gravitational forces exerted by planets like Neptune are crucial in maintaining Pluto's orbit, preventing further chaos in the system. Despite its irregular orbit, Pluto's path has remained surprisingly stable over long periods, thanks to the gravitational influence of neighboring planets. While 6 minutes and 34 seconds mathematical models and simulations play a key role in forecasting the movements of celestial bodies, they also reveal the complexities of gravitational interactions. Although Pluto's orbit may be unpredictable over centuries, it remains relatively steady in the broader context of the solar system's gravitational framework. While the likelihood of a Pluto-Neptune collision remains low, it serves as a reminder of the unpredictable nature of the cosmos. The warning from experts like Tyson and Kaku emphasizes the constant flux of the 7 minutes and 5 second solar system. While such a collision seems unlikely in the near future, it underscores the delicate balance of forces governing the movement of celestial bodies. Beyond its scientific importance, the study of Pluto holds practical significance for future space exploration. NASA's New Horizons mission, launched in 2006, provided us with unprecedented images and data from 7 minutes and 40 seconds Pluto and its moons during its historic flyby in 2015. These findings revealed new details about Pluto's surface, including vast frozen nitrogen fields and expansive water ice plains, expanding our understanding of geological processes on distant worlds. The success of the New Horizons mission also demonstrated the importance of international collaboration in exploring distant celestial bodies. By studying Pluto, scientists have gained valuable insights into the outer reaches of the solar system, which could guide future missions to other distant objects. The ongoing debate over Pluto's status as a dwarf planet reflects larger questions about the classification of celestial 8 minutes and 11 seconds bodies. Despite the fact that Pluto satisfies a number of the requirements for a planet, its reclassification stokes important debates about the development of science and the classification of astronomical objects. Examining Pluto's orbit and its interactions with other planets improves our comprehension of planetary motion, celestial mechanics, and the formation of the solar system. By studying Pluto's unique orbit, we can better understand the dynamics of other distant celestial bodies in 8 minutes and 43 seconds the Kuiper Belt, a region beyond Neptune populated by small icy objects. Research into Pluto's orbit offers clues about the gravitational forces that may have influenced the early formation of planets. This knowledge is essential for developing theories about the solar system's origins and the processes that shape planets over time. Although the 9 minutes and 15 seconds likelihood of a Pluto-Neptune collision is low, it serves as a reminder of the unpredictable nature of space. As we continue to explore the outer solar system and beyond, the study of planetary orbits and celestial dynamics will remain a core area of research. The Pluto story is a testament to the power of scientific inquiry and the enduring quest to understand the mysteries of the cosmos. While the likelihood of a Pluto-Neptune collision remains low, the study of this possibility highlights the unpredictable nature of space and the complexities of celestial mechanics as we continue to explore the outer reaches of the solar system and beyond. As astronomers continue to study Pluto and its interactions with Neptune, new questions emerge about the long-term stability of the outer solar system. While the 2:3 orbital resonance ensures that Pluto and Neptune never collide under current conditions, could external influences, such as passing stars, rogue planets, or even dark matter, alter this delicate balance over millions or billions of years? The unpredictable future of Pluto's orbit. While computer simulations have shown that Pluto's orbit is stable for at least a few billion years, some astrophysicists argue that unpredictable cosmic events could introduce new variables. For instance, if a passing star from another system were to exert gravitational force on the outer solar system, it could slightly perturb Pluto's orbit. Even the gradual shifting of the Sun's mass over time, as it loses material through solar winds, could subtly affect orbital mechanics. Some theories also suggest that dark matter, the invisible substance believed to make up most of the universe's mass, could influence planetary orbits in ways we have yet to understand. If dark matter exists in higher concentrations in certain areas of the galaxy, its gravitational effects could create long-term orbital shifts in celestial bodies like Pluto and Neptune. A cosmic domino effect. If an external force were to disrupt Pluto's orbit significantly, it could create a domino effect. Pluto's interaction with Neptune would be the first to change, but other outer solar system objects, such as Kuiper belt objects and even Neptune's own moons, could be affected as well. This, in turn, might slightly alter Neptune's orbit, which could then subtly impact Uranus, setting off a chain reaction throughout the solar system. Some researchers speculate that this kind of orbital shift could eventually affect Earth, though only after an immense timescale of millions or even billions of years. While a direct collision between Pluto and Neptune remains unlikely, the idea that planetary orbits are not entirely static reminds us of the ever-changing nature of the cosmos. The search for more clues. To better understand Pluto's orbital stability, scientists continue to rely on advanced simulations and observational data from telescopes like the James Webb Space Telescope, JWST. New missions are also being proposed to explore the Kuiper belt in greater detail, potentially uncovering additional clues about how planetary orbits evolve over time. Meanwhile, researchers are looking at exoplanetary systems, distant star systems with their own planets, to see if similar orbital resonances exist elsewhere. If astronomers find other dwarf planets locked in orbital dances like Pluto and Neptune, it could provide a broader context for understanding the rules governing our own solar system. A universe of unanswered questions. As humanity continues to explore space, Pluto's story remains a compelling case study in celestial mechanics. Whether it's the lingering debate over its planetary status, its mysterious geology, or its unique orbital relationship with Neptune, Pluto continues to remind us that the universe is full of surprises. While a Pluto-Neptune collision remains an unlikely scenario in our lifetime, studying such possibilities pushes the boundaries of our understanding and prepares us for future discoveries. As space exploration advances, perhaps one day we'll uncover new insights that reshape our entire perception of planetary motion and the fate of the solar system. For now, Pluto remains a frozen enigma on the edge of our cosmic neighborhood, a small but significant reminder that in the vastness of space, even the tiniest celestial bodies play a role in shaping the grand ballet of the cosmos. A disruptive force on the horizon? While Pluto's orbit remains stable for now, astronomers are beginning to consider how external cosmic forces could disrupt this delicate balance. Recent simulations suggest that if a rogue planet, or even a wandering brown dwarf, were to pass through the outer solar system, it could exert enough gravitational force to alter Pluto's trajectory. Some researchers speculate that a yet undiscovered Planet 9, a massive theoretical planet lurking in the outer reaches of the solar system, could already be affecting the orbits of Kuiper belt objects. If this mysterious world exists, its gravity might one day shift Pluto's resonance with Neptune, setting off a slow but inevitable chain reaction that could destabilize Pluto's orbit. Even more intriguing is the possibility that interstellar objects, such as the mysterious Oumuamua, could enter the solar system and disrupt the gravitational equilibrium. If a sufficiently massive object were to pass close to Pluto, it might perturb its orbit just enough to increase the risk of an eventual collision with Neptune. A catastrophic encounter. If Pluto's orbit were to shift dangerously close to Neptune's, the first warning signs might be subtle. Tiny deviations detected by space telescopes like JWST or upcoming interstellar observatories. Astronomers would have only a limited window of time to predict the long-term consequences. A direct collision between Pluto and Neptune would be catastrophic. Due to its smaller size and icy composition, Pluto would likely be torn apart by Neptune's immense gravitational forces before impact. The resulting debris could scatter across the outer solar system, potentially striking Neptune's moons or even altering the planet's own orbit. Some fragments might be ejected into deep space, while others could be pulled inward toward the Sun, creating a new generation of comets that could eventually pass near Earth. The event would offer an unprecedented opportunity to study high-energy cosmic collisions, but it could also introduce new instability into the solar system's gravitational dynamics. A race against time. If scientists detect a potential orbital shift early enough, is there anything humanity could do to prevent it? The idea of planetary-scale intervention may sound like science fiction, but with rapid advancements in space technology, it might not be impossible. Some theorists propose that a well-placed gravitational assist, perhaps by redirecting an asteroid to pass near Pluto, could slightly adjust its orbit and maintain its current resonance with Neptune. Others suggest using nuclear propulsion or solar sails to subtly nudge Pluto's path over centuries, a process that would require precise calculations and long-term monitoring. Would humanity have the capability, or the will, to intervene in such a cosmic event? Or would we be forced to watch as Pluto's fate unfolded, a reminder that even in the vastness of space, celestial bodies are never truly safe from change? The fate of Pluto, a cosmic mystery. For now, Pluto remains in its stable orbit, locked in its celestial dance with Neptune. But as we continue to explore the outer solar system, new discoveries could reshape our understanding of planetary motion and the hidden forces that govern our cosmic neighborhood. Pluto's story is far from over. Whether it remains a distant, icy wanderer or one day faces an uncertain fate, its unique orbit will continue to captivate scientists and space enthusiasts alike. The study of Pluto and its interactions with Neptune reminds us that even the most distant corners of our solar system are part of a larger, ever-evolving cosmic story, one that we are only just beginning to understand.